Like, we've got a difficult topic here, this implicit differentiation. We're going to do a few more examples, and hopefully, if the big idea didn't quite click, that you can at least kind of do the questions that way. Okay, so here's a question. In the 40s, commercial airliners had square windows, but the harsh wind angles meant that the surrounding metal experienced pressure 2-3 times greater than elsewhere, and the cabin designers started using a super ellipse. So this is the shape that you might recognize from an airplane. In the first quadrant, the equation is given by this. Now so what does the first quadrant means over here? I'm not sure what's happening. Oh, it's a bit more complicated for the other regions. So this is the first quadrant. So this part of the curve is defined like this, okay? So the first thing is use implicit differentiation to find dy dx, and then we'll probably have other questions as well to consider. So we'll just write down the equation on the next page. X to the 5 over 2, y to the 5 over 2 equal to 1. So yeah, so first of all, in this implicit differentiation, in the first quadrant, it's the graph of a function, so we can write y is y of x. So we write x to the power of 5 over 2 plus y of x to the power of 5 over 2 is equal to 1. Okay, and now what we're going to do is we're going to differentiate both sides with respect to x. So if we do that, now x to the power, how do you differentiate a power? You multiply by the power and reduce the power by 1, and 5 over 2, which is 2.5, take away 1 is 1.5, which is 3 over 2, plus. Now for the y of x to the power of 5 over 2, you're going to need the chain rule. So the outside function is x to the power of 5 over 2. So the derivative of x to the power of 5 over 2 is 5 over 2, x to the power of 3 over 2. That's the first part of the chain rule. The second part of the chain rule is you evaluate at the inside, and then the final part of the chain rule is you multiply by the derivative of what's inside. Now we don't know what y of x is, so all we can say about the derivative is that it's dy dx. Equal to the derivative of 1, which is just 0. So we have an equation now on x, y, and dy dx to solve. So what I'd probably do here is take away the 5 over 2 x to the 3 over 2 away from both sides, and say the 5 over 2 y to the power of 3 over 2 times dy dx is equal to minus 5 over 2 x to the power of 3 over 2. And then all you want to get rid of is the multiplication by this. So divide both sides by exactly that number. And so you'll have dy dx is equal to minus 5 over 2 times x to the power of 3 over 2 divided by 5 over 2 times y to the power of 3 over 2. And if you want, you could divide up and below by 5 over 2. Okay. So going back to the question, so we found dy dx, that's good. And the second thing is find the equation of the tangent to the curve at this point here. Now we might just remark that from the picture we can kind of estimate what our answer should, well, is there anything we can say about our answer? So, well, where is the x coordinate equal to the y coordinate? Around here. And look at the slope. The only thing we're going to expect is that the slope is negative. And we should expect as well that, because this is the point 1, we should expect that, so it'll be y equal to mx plus c. We'll expect the m to be negative, and we'll expect the c to be bigger than 1, because this is 1 and this is going to go higher. It's going to cut up there much higher. Okay. So now, is it looking for the equation of the tangent? Yes. So we're going to do our y minus y1 business. So let's write that down. So y minus y1. Now the y1 is 0.7579 equal to the slope. Now to find the slope, we're interested in the slope at the point x equal to 0.7579 and y equal to the same thing, 0.7579. And we can bang that number into this But because if you look at it, it's the same. Well, there's a minus, and it's a number divided by itself is 1. So the slope is going to be -1. As we said, we'd expect it because the tangent is going down. So the slope there is -1 times x minus x1. So this is y minus y1 equal to m, which is the derivative evaluated at the point, times x minus x1. y1 and x1 are the same. They're given by these coordinates here. And so what I recommend is you multiply out the right-hand side. So I get -1 by x is minus x, and -1 by that number is plus 0.7579. And what I need to do then is add the 0.7579 to both sides to get y on its own. Y is equal to minus x, 0.7579 plus itself, plus 1.516 if I'm just going to go to 4 significant figures. So as expected, bigger than 1. The constant is bigger than 1. Okay, so that's that, done. Right, another question. So this trisectrix of Maclaurin is given by this formula here. And it says use implicit differentiation to find dy dx. Okay, yeah, same crack. Now there is options here. Okay, well, let's pause for a second. Okay, so we'll find dy dx for this, and then we'll find the equation of the tangent line. So the equation, so if you're near a particular point, so actually this one is colored. I don't know, are they the branches? It's hard to say. It's probably not like that, but certainly say if you're near this point, if you're close enough to that point, that's just the bit that we colored is part of the graph of a function y is equal to y of x. And so I can rewrite the equation above with, instead of y of x. So we have y of x squared times 1, this is just rewriting the equation except with y of x instead of y. It looks a bit weird, I'll just have another look. Yeah, that's it. Right, so we differentiate both sides with respect to x. So first of all, on this we have a little product rule, u and v. The rest of it is a bit more straightforward. So differentiating both sides with respect to x. So the product rule says it's the first thing, which is y squared. I only have to write the y of x once, times the derivative of the second thing. The derivative of 1 is 0 plus the derivative of x is 1. Plus the second thing, which is 1 plus x, times the derivative of y of x all squared. Now, y of x all squared, the outside function is x squared, and what am I trying to say here? The chain rule says you differentiate the outside is x squared, so derivative of x squared is 2x. The chain rule then says you evaluate at the inside, and then the chain rule says you multiply by the derivative of what's inside. And all you can say about the derivative of y of x is that it's dy dx. Okay, now just in terms of the product rule, that was the first thing by the derivative of the second thing plus the second thing by the derivative of the first thing, plus the derivative of x cubed, which is 3x squared, minus, now when I'm different, now a lot of the time you would be doing like minus 6x. I'm always going to fix the constant, and you'll see why for later on. So I'm going to fix the minus 3, and the derivative of x squared is 2x equal to 0. Now our job is to solve this now for dy dx. So what I'm going to do first is I'm going to, now I want to get all the dy dx on one side. I'm going to, that's not what I wanted. That's y squared. I'm going to take that away from both sides, and I'm going to take that away from both sides. So if I do that, I end up with, so here I got 1 plus x by 2y. I can write, now that's a number 1 plus x by 2 by y. I can write it whatever order I want. So how about 2 by 1 plus x by y times dy dx equal to So the first bit is y squared, take that away from both sides. Then take the 3x squared away from both sides, and then the minus 6x, add 6x to both sides. And now all we have to do is get rid of the multiplication by this, and we get rid of that by dividing both sides by that number. So you get dy dx equal to minus y squared minus 3x squared plus 6x divided by 2 times 1 plus x times y. So that's the derivative. So that's the first bit done. And then they're interested in the equation of the tangent line at 1, 1. So again, if we have a picture, we should use it. You won't necessarily be given a picture, but it's good if there is one. So that's the point here. And so the tangent looks something like that. So the m is going to be positive, and the c is probably between 0 and 0.5. See where it's cutting? Between 0 and 0.5. Okay, so that's what we expect to see. If we don't get that, we probably made a mistake and we'll have to go back and check what we did. So the equation of a line is y minus y1 is equal to m times x minus x1. We're interested, the question tells us at that point 1, 1. So we know that x1 is 1, y1 is 1. What we have to do is find the slope. And the slope all day long is the derivative. And we're interested in this at x equal to 1, y equal to 1. So what we have to do is substitute x equal to 1, y equal to 1 into the derivative. So we'll get minus 1 squared minus 3 by 1 squared plus 6 times 1 all over 2 times 1 plus 1 times 1. So this will have to be positive. So on top I see minus 1 minus 3, that's minus 4, plus 6 is 2, and on the bottom I see 2 by 2, which is 4, so that's a half. So if we look back, it's good that it's positive, and the slope of this is supposed to be a half. And just kind of, I think we're going to find that the c is actually equal to a half. Again, I can't draw tangents. Okay, so we find the equation of the tangent line, y minus the y coordinate that we're interested in is 1, equal to the slope, which is a half, times x minus x1, which is 1. So as usual, multiply out the right hand side, half x minus a half, and then get rid of that minus 1 by adding it to both sides. So y is a half x plus a half, which does stack up quite well with the picture. Okay, so here is a different type of question. So what have we got here? The exponential function can be defined as the solution of the ordinary differential equation. In other words, it's saying that e to the x, the exponential function, is the thing that when you differentiate it, you get the same thing. Okay. The natural log then is defined as the inverse of that. So if you work with inverses, if y is equal to log of x, let's see, how does this work? So basically the idea is that if you have, I'm going to use just a and b here, a and b. So if, for argument's sake, the exponential function sends a number a to a number b, the log will send you back the log function. Okay, so this is saying that, it's a bit hard to see this, but this is saying that the exponential function, we'll take this, just to explain this a bit. It's starting with y, and if you do e to the y, you get to x. Now you don't actually have to understand all of this, strictly speaking, to answer this question. So then if you take the log of x, that will give you y. Their pictures, those green pictures, are like what we drew earlier with the inverse of a matrix. Exactly similar idea. Okay, so this is just explaining how you find the derivative of log of x. So you have the derivative of exponential is basically, can be defined as the thing which is its own derivative, and then you can say the log is the inverse, so you end up with this, and this is where we'll kick off. And then the thing is, use implicit differentiation to find dy dx. Now, what is y? Y actually is log. So let's see how this goes. So you can kind of follow the thing that's going on, or you can just answer the question. If you just zoom in on the question, it just says use implicit differentiation to find dy dx if x equal to e to the y. So you don't, strictly speaking, have to understand all the theory here. So as usual, write y equal to y of x. So you've got x is equal to e to the y of x. Now it might be a bit harder for you to see that this is a chain rule. So one way of seeing that this is definitely a chain rule is to write the e to the power as exponential of. And here you can better see the inside and the outside. Okay, I'm just looking, sorry, I'm just going ahead here because I see space. Okay, so we're going to need more space for part 1. So differentiate both sides with respect to x. The derivative of x with respect to x is 1. Now what about the thing on the right hand side? You've got an inside and an outside. So that means chain rule. The outside function is exponential, and the derivative of exponential is itself. Now I'm going to write it as e to the power, because that's usually how we write it. So the writing, in other words, what I'm trying to say is just including this to help you see the chain rule. Normally you just say, oh, the outside function is e to the power. So the derivative of e to the power is itself, which I kind of am ready to write here. So there's e to the power. And then the chain rule says evaluate at the inside. The inside here is y. And then times the derivative of what's inside. And all you can say about the derivative of y of x is that it's dy dx. Okay, and now to solve for dy dx, all we have to do is get rid of this e to the y. So all you have to do there is divide both sides by e to the y, and you end up with dy dx is equal to 1 divided by e to the y. And then part 2, or part b I should say, says hence use the fact that e to y is equal to x to write down the derivative log x in terms of x alone. Dy dx is equal to, well, what's e to the y? Just says it there, e to the y is x. So that's how you show that the derivative of log is 1 over x. Okay, it's difficult stuff. There's no two ways about it. We'll do another example like that one. Okay, so consider the function y equal to x to the x. And then what we're going to do is take the log of both sides to show this. Then use implicit differentiation, and then substitute in the y equal to x to x to finish off. So the good thing about this is it kind of helps, it's kind of done step by step. So starting with y equal to x to the x, we're going to take the log of both sides. So we get log of y is equal to log of x to the x. Now I know you would have done some stuff with logs last semester, and one of the properties of logs is that they turn powers into multiplication, and that would be in the tables that I send you. Okay, so what am I saying here? I'm saying, now while I'm here, I'm going to write the y as, well, I better not write it yet, but so you get log of y equal to, so this to the power of x gets turned into multiplied by x. So the power of x gets turned into multiplied by x, and that's what we were asked to show. And now we're going to use implicit differentiation. Now I'm just going to write the log of y as log of y of x to help me see the chain rule. Okay, so we're going to differentiate both sides with respect to x. So differentiating the right hand side, as I said, we have a chain rule, because we got, it's not log of x, it's log of a function of x. So you have to use the chain rule here. And the chain rule says differentiate the outside function, and the derivative of log is 1 over. We just showed that in the last example. And the chain rule says evaluate at the inside. Well, the inside here is y times the derivative of what's inside. Okay, And now we must differentiate the right hand side, and it's x times log of x, so it's a product rule. So we get the first thing by the derivative of the second thing. The derivative of log of x, we just showed, is 1 over x, plus the second thing, which is log of x, times the derivative of the first thing, and the derivative of x is 1. And now the first thing there is x by 1 over x, which is x divided by x, is just 1. And so to solve for, let's say, to find dy dx, all we have to do is get rid of this 1 over y. So to get rid of that's a divided by y, to get rid of that, what we have to do is multiply both sides by y. And when I say both sides, we might be a little lost here. Multiply that by y and multiply that by y. So multiplying the left-hand side by y, we'll get rid of the division by y, we'll have dy dx. And multiplying the right-hand side, we'll have y. Now if you write y, 1 plus log of x, that's dodgy, because BEMDAS, only the y is multiplying the 1 the way it's written. You need a bracket there. Okay. And then what's the last thing? Substitute y equal to x to the x into the previous part. So all you have to do now is just, therefore, the derivative of x to the x is, so just put the y equal to x to the x and you're done. Now I'm not going to pretend that this implicit differentiation is easy. It's not. If you're following it, well done. You're going to have to try and do questions. That's how you're going to learn, and you're going to send on the questions. Now what I have in this chapter is that I have the questions are what are called interleaved. So they're interleaved. So you're going to have stuff from the previous sections in here, and that should help you. So you just keep trying doing questions. So you do question 1, so that's implicit differentiation. Question 2 is implicit differentiation. Question 3 is, question 4 then is parametric. So you're kind of getting revision as you go. Question 4, that was question 4, yeah. Then question 5 is more implicit, more implicit, more implicit. Yeah, so it's not that much interleaving, but this is the idea. Okay, so good luck with this stuff.